what are the different elements of the embedded system. So if you take the embedded system, what that particular embedded system consists of. Okay. So if you take the embedded system, mainly it is consists of single chip controller. A controller should be there, which will be acting as a brain of the system. Next is memory that is embedded firmware. So the firmware is nothing but what? It is going to hold the software, which is uh, loaded into the which is loaded into your read-only memory. So it is burned into a read-only memory. So a typical example of this particular memory is your BIOS. Okay. So next is input sensors will be there, output ports will be there, which will be acting as a counter action which you need to take for the input what it has been coming. Okay. Next is communication interface. So even if only if and only if you have the communication interface, uh, you can do the communication with the external world. So and then depending upon the different functionalities which you are going to have, other supporting ICs and subsystems will be there, because you are not going, even if you want to do one particular task, some other IC should be there to work with that one. So like a decoder should be there, encoder should be there to encode and decode, or some other operations if you want to perform, like you have seen in your ADE that how it will be designed. Okay. So next, when it comes to the core of the embedded system, so let us see one by one what are the different components of your embedded system. This particular question is important for your examination point of view. Okay. So what are the different elements of the embedded system? So mainly the embedded system consists of the following parts: six. That is your core element, that is core is there. That is a single chip controller which will be acting as a brain of the system. Next is memory should be there, which will be holding the piece of the software into the ROM, which that particular application has to be performed. Third is your input port should be there. So it will be acting as a sensor, so where you are going to place the sensors there, and you are going to have the output ports. So output ports are whatever the input you are going to get. So the corresponding action has to be taken at the output. For that particular reason, you are using the actuators. So fifth one is communication interface you should have. Next is other supporting ICs and subsystem. So when it comes to the core of an embedded system, okay, so either embedded system which you are going to design, either it may be a application specific or domain specific. Okay, so if you are embedded device, or either it may be a domain specific or application specific devices, which are built under central core. That means if you have the core, that is single control, which is going to have the core is nothing but what? CPU. Okay, so here the microcontroller will be acting as a core. So now, which will be built under center core. Okay, the core of the ICs, which are embedded system, which you are going to have, it is going to fall under certain categories. What are these categories? The first categories which you are going to have is general purpose and domain specific processors. So if you start talking about general purpose and domain specific processors, so under that you are going to have microprocessor and microcontroller and digital signal processors. So now these are the core elements which you are going to use for general purpose and domain specific processing. Okay. So what are there? There are microprocessor, microcontroller, digital signal processor. So the second one which you are going to have as a part of the core is application specific ICs. That is application specific integrated circuit. So you are going to have the integrated circuit which will be designed to do a specific operation. Okay. So the third one is programmable logic devices. So this part you have been read already, PLDs in your ADE. The same thing will come here also. So the programmable logic devices you are going to have, PLDs you are going to have. Yeah, so we are going to have the PAL, that is a programmable programmable logic array. We have been discussed, and you have discussed about PROM, that is programmable read-only memory. So those things will also be used in your core of the embedded system. So now the fourth one is commercially off-the-shelf components. The fourth type of the core which you are going to have is commercial off-the-shelf components. Okay. So next, when it comes to the general purpose and domain specific processors, so we'll discuss one by one. So when it comes to the general purpose and domain specific processors, so here we are going to have microprocessors. Next, we are going to have the general purpose microprocessor, so which you are going to use in your day-to-day life in your normal system, normal computers, or it may have the ASIP, that is called as application specific integrated instruction set processors. That is that will be ASIP. So GPP stands for general purpose processor. ASIP stands for application specific instruction set processor. As the name indicates, application specific instruction set processor. So it is this particular processor is going to work with respect to particular application. Okay. So next we are going to have the microcontrollers. So next we are going to discuss with respect to the difference between microprocessors and the microcontrollers. This already we have been discussed. So this I have to discuss with respect to the topic point of view. So I don't want, I will skip this particular part since this particular module is vast. So I will skip whichever you people have already read. Okay. So now next is digital signal processors. So next is when it comes to the processor. So we have gone with different types of processor, right? One is RISC processors or controllers. Second is hardware processors, Newman processor or control architecture. Next is big endian or little endian processors or controllers you are going to have. Next, you are going to have the load store operation and instruction pipelining. So this we have already discussed, I think, right? So all of you know what is the difference between RISC versus CISC processors. Can anyone tell what is the difference between RISC and CISC? Can anyone tell? What do you mean by RISC? RISC stands for Reduced Instruction Set Computer. CISC stands for Complex Instruction Set Computer. Okay. So next comes to the microprocessor. So now, if we talk about the microprocessor, almost 80% of the embedded systems are processor control based. So if you take even the market, so most of the time, so the most of the microprocessor or microcontroller which are going to get in the market, so almost 80% of the embedded system are going to use the microprocessor or microcontroller. Now the processor may be either microprocessor which you are going to have, or the microcontroller, or digital signal processor. Okay. So now how we are going to decide when I have to use the microprocessor, how I have to decide when I require the microcontroller, or how I have to decide when I have to use the digital signal processor. So now it depends upon the type of the domain and application which you need to build. Okay. So you need to build some application, or you need to have some domain where you have to work on that particular application or that particular component. So then you have to, depending upon that that particular application or that particular domain, you need to decide that using what core I can efficiently build that particular system. Whether if I use the microprocessor, it will be efficient. Whether if I use the microcontroller, whether it will be efficient, or whether it will be a DSP, that is digital signal processor. If I use it, it will be efficient, depending upon the type of the application or domain which you are going to design the embedded system. So now first, when it comes to the microprocessor, so the already we know what you mean by microprocessor, right? So we have already seen in your first module itself. So a microprocessor, it is nothing but what? It's a single silicon chip. Okay. So if it is a silicon chip, what it will be having? So it is a silicon chip representing a central processing unit. Okay. So a microprocessor will be having, microprocessor is a silicon chip or electronic device. If we take an electronic device, the electronic device is made up of silicon only. So if we take the normal any device, if it will be made up of transistor. In turn, the transistor is made up of your silicon chip or silicon. Okay, that is nothing but your silicon substrate. It is going to be built. So that's why most of the times the microprocessor is called as silicon chip, because it is developed under silicon substrate. Okay, so normally germanium they will not use much, but most of the time they are going to make use of the silicon only. That's why it is called as a silicon chip. Okay, so your microprocessor is a silicon chip representing what? Representing a central processing unit. So now when you are going to have the CPU, already we know that what is the operation that particular CPU is going to do. So that particular microprocessor is going to able to perform arithmetic and logical operation. Okay, arithmetic and logic operation depending upon according to the predefined set of instructions. Because as a user, I would have written the instructions we have seen in the program. So step by step, I'm going to write the program. I'm going to instruct to the microcontroller that these are the sequence of work which has to be done. Okay, these are the sequence of the work which has to be done. So now, whenever you are going to have the predefined set of instructions, so all the instructions if you are going to have, so that is specific to the manufacturer. So that you have to keep in your mind. Either if you take any microprocessor or microcontroller or data signal processor, whatever the instruction set is there for that particular processor, so that will be specific. That will be specific to that particular manufacturer. So for that particular reason only, when you want to take any processor, if you want to build any application, first you have to see what are the features which will be provided that particular microprocessor manufacturer, that you have to look into. Now, whatever the CPU you are going to have, the CPU contains what? The CPU contains the arithmetic and logic unit. So the CPU contains arithmetic and logic unit, control unit it is going to have, and working registers you are going to have. So this we have been already seen in your ARM. Okay. So CPU contains the ALU, control unit, and working registers. So now when it comes to the microprocessor, so it is a dependent unit. Okay. So if you take the microprocessor, it is a dependent unit. Why it is called dependent unit? Because if the microprocessor has to work, some other additional component has to be combined, joined together. So it is added to some additional hardware has to be combined together to make that particular microprocessor to work efficiently. So that we have already seen in the difference between your microprocessor and microcontroller. Okay. So now what it contains, what are the dependent unit it requires? So the dependent unit which requires the combination of other hardware like memory, timer unit should be there, and interrupt controller should be there for proper functioning. Okay. So that's what. So now when it comes to the developers of microprocessor, who are the developers of the microprocessor? So who is going to build the first microprocessor? The first microprocessor is built by the Intel. Okay. Okay. Intel claims the credit for first development for the credit for developing the first microprocessor unit. Okay. So the name of that particular processor is Intel 4004. So Intel is the first microprocessor unit which is developed. Okay, and it is a 4-bit processor. Your Intel 4004, which is a 4-bit processor, it is a 4-bit processor, and it was released in year 1971. So the 4004 microprocessor, which is designed by Intel, and it came into the market in the year 1971. So that is where the first microprocessor was came into the market. So now if you take the n number of microprocessor, okay, they are in the, if you go with the generation of microprocessor or which you are going to have. So now here you are going to have Intel. So Intel 4004, so it is developed in November 1971, which is of 4-bit. So next comes the Intel 4040. Okay. So next it is the advanced version of 4004. So even if this one is having 4-bit. So next comes the 8-bit microprocessor. So the 8-bit microprocessor, where it is when it is started is in 1972. So the number which you are going to have is Intel 8008. So your Intel 8008 is the microprocessor which is came into existence in 1972. So it is going to have the 8-bit CPU and a external 14-bit address bus. Okay. So it can address up to 14-bit address. That is the total number of memory location which it can hold is 2 power 14, the number of address. Because this particular 8008 is going to have the 14-bit address. Okay. So address is different and bit is different. So when you talk about the 8-bit CPU, the size of the register will be 8-bit. Okay, you understand it. That means the register can hold the maximum value of up to 2 power 8. The register can hold only the maximum value of 2 power 8. So, but the same thing not be there for your address bus, because address is going to tell you that how many number of memory locations are there. So it will going to have the 14-bit address bus. So if you take the address bus of 14-bit, so it is going to generate the address of up to 2 power 14. Okay. So that many addresses will be there inside that particular microprocessor. If that many addresses are there means what? It is going to have that many memory locations. So the number of address depends tells you what? The number of memory locations which is residing inside that particular microprocessor. Okay. So next is Intel 8080. So you're going to have this particular 8080 in the year April 1974 with additional feature for your edge. It's the additional feature for your 8008. Okay. So in this one, the instruction set may differ. So if you take the 8080, so the instruction set may differ. So here in 8080, what happened is, so the data bit which you're going to have in this one is 8-bit, whereas the address bit which you're going to have is 16-bit. So as I told you that 8008, it is 14-bit address bus. In 8080, it is a 16-bit address bus. You have to keep it in mind, that one. Okay. So what's the difference between 8008 and 8080? Since it is having the 16-bit address bus, it can have more number of memory space. Okay, if you have the more number of memory space, inbuilt processor, it can hold more amount of data. Since I have already explained you that one memory location is going to hold one memory location is going to hold 1 byte of data. Okay, one memory location is going to hold one byte of data. So the next is Motorola. Motorola 6800 is came into existence. Next, the Intel released 8085. Okay, 8085 came into existence in 1976. After 8085, Zilog. Zilog is Z80, which you are going to have. And in the July 1976, it came. So now after that one, it came the 8086. So like 80386 came into picture, 80186 came, 80286 came, 80386 came, 80486 came. So you can see it here. Okay. So if you take, so later generation is 80186 came, and 18386 and 80286 came. Okay. And then later 80386 came, and later you're going to have 80486 came, and next it is 80586 came. It is nothing but your advanced version of 8086. Okay, so that is, it is the first version of 8086, second version of 8086, third version of 8086, fourth of 8086, fifth of 86. So this is where your 5 refers to Pent. Okay, so this is where from where your Pentium processor starts. This is from where your Pentium processor starts. So it is nothing but 80586. The processor name, the processor which you are going to have for Pentium processor is 80586. Since 5 refers to Pent, since the 5 refers to Pent, that's why the number 80586 processor is called as Pentium processor. Now with the advancement, you are going to have Pentium processor like Pentium 1 came, Pentium 2 came, Pentium 3 came, Pentium 4 came. So now it is already i3, i7 is there. Like octa-core, that is a single core will be there in a single day. Octa-core is there, dual core is there, and quad core is there. These are some of the processor which you are going to have. So with the advancement of the 886, okay. So with the advancement of the 886, so your Pentium processor started. So now, when it comes to this is what how the developer evolution of microprocessor came. So next, when it comes to the general purpose, our application specific instruction set processors, which are going to have. Now here, whatever the processor you're going to have, the processor is designed for to do some general computing task. Here, the processor is going to design for computing the general computing task. So basically, this particular type of microprocessor is used for general market, where the high volume is required, where the volume required is high, due to which the cost will be low compared to the application specific instruction set processor. So it's basically used for the general market. So if you take the general purpose processor, it also contains the ALU and control unit. So arithmetic and logic unit and control unit. If you take any processor, okay, so if you take any processor will be having its own arithmetic and logic unit and its control unit. So next, when it comes to the application, then it comes to the application specific instruction set computer. So these are processor with architecture and instruction set. So now in this one, as the name indicates, application specific instruction set processor. Okay. So now this particular processor came with a specific architecture and specific instruction set. Okay. So it is optimized and designed to work for that particular application only. Like, so if you take the application specific instruction processor or the processor with architecture and instruction set optimized for specific purpose. Okay. If you take the ASIP, it is designed, that particular processor is designed to do some specific operation. So what are the different operations it is going to perform? It is going to be used in networking, telecom, automotive, media applications, and control applications. Okay. So next, with the needs of application-specific instruction processor arises. So now, when general purpose processor is unable to meet the user requirement. So when the general purpose processor is not able to meet the requirements of the uh, specified purpose, the need of the application specific instruction processor came into existence. Okay. So after that one became your microcontrollers, DSPs, that is digital signal processor, and system on chip. These are some of the examples of application specific instruction processor. If you take the microcontroller, even the microcontroller, you have to program it. So you are going to program the microcontroller to do a specific task, or we are going to embed the software to work for a specific application. Okay. So next you are going to have the digital signal processing. So that is you are going to use for digital signal processing. And third one is your system on chip. So these are the examples for application specific instruction set processor. Okay. So next comes the microcontroller. This you have already seen that one. So what the microcontroller contains? A microcontroller contains it is also a silicon chip. So that, but it contains what? It contains the CPU, internal RAM, and specific registers arrays. On chip ROM will be there. Memory for program storage will be there. Timer and interrupt control units and dedicated IO ports. All these are combined and embedded into a single chip. Right? This is what the difference between your microprocessor and microcontroller. So this we have already been seen there. Okay. So it contains CPU, RAM is there, specified register arrays will be there inside your microcontroller, that is the inside that chip only, and your on chip, that is inside the IC only, you are going to have the ROM or flash will be there, flash memory will be there for program storage, and the timer and interrupt control units and dedicated IO ports, which will communicate with the specific devices. So now if you take the microcontroller, they can be considered as a superset of microprocessors. So now microcontroller are considered as the superset of microprocessor. So when it comes to the microcontroller, so microcontroller can be a general purpose or application specific. Okay. So like Intel 8051. So if you take the Intel, there are many microcontrollers are there. So the microcontroller can be used for general purpose also, and the microcontroller can be used for specific applications also. So if you take the microcontroller, which has been used for general purpose, okay. So what are they? It will be like Intel 8051 is one example, which is it is designed for generic applications and domains. So if you take the application specific, like automatic voice response is there from Atmel corporations, designed specifically for automotive applications. So now here AVRs are nothing but what? Automatic voice response. So depending upon your voice, what you are going to have, the vehicle has to respond. AVR systems which you are going to have. So these are the things which are going to have in microcontrollers. So now if you take the microcontroller, so microcontroller contains all the necessary functional blocks for independent working. They found greater place in embedded domain, and it is cheap, cost effective, and readily available in the market. So if you go to the market, you can buy a microcontroller for 100 rupees or 150 rupees. That is available. If you go for SP Road and if you if you check it for 8051, so then you will get 8051 now different depending upon the different manufacturer. So you can get that particular microcontroller for about even for 70 rupees also you will get up to 150, 100, 150 depending upon the quality of the microcontroller or the manufacturer. Okay, so you can get that particular, that is cheap in price, and you can build your own embedded system. Okay, so you can build the whole embedded system. That will take it as one task. So if you take one task and you once the lockdown is releases, you go to the SP Road and you purchase the 8051 and you design your own embedded system for a particular task, like voice recognition also, or it may be you rover also you can design it so that it will be moving inside your home, like you can do the vehicle dragging also you can do it. Okay. So if we take the microcontroller, so TMS 100, TMS 1000 is the considered to be the first microcontroller. That is from Texas Instrument. Okay. Texas Instruments TMS 1000 is considered as the first microcontroller. So next, when it comes to the difference between microprocessor and microcontroller. Okay. Once we have discussed about the microprocessor and we have discussed about the microcontroller, the same thing is repeated. Now almost you have know this particular thing already. So your microprocessor is nothing but what? It's a single chip. So representing a central processing unit, which is capable of performing arithmetic as well as logical operation according to predefined set of instructions. So as we have announced that your microprocessor contains requires the external dependent unit, right? So we are told that the microprocessor requires the dependent unit. So it requires a combination of other chips like timers should be there, program and data memory chips should be there, interrupt controller should be there for functioning. Whereas in your microcontroller, what will happen? Inside a single chip itself. So it is a microcontroller itself is a highly integrated chip. Okay, that contains what? That contains the CPU, scratchpad, RAM, special and general purpose register RS. Okay, on chip ROM or flash memory for program storage, it will be there. And timer and interrupt control units and dedicated IO ports will be there. And it is a self-contained and does not require any external input interrupt controller. So it is whatever the unit is going to have, it is a self-contained unit and it does not require any external interrupt controller or timer or UART etc. for its functioning. So most of the time, general purpose is in design and operation, mostly application oriented or mostly the microcontroller are used in the field where you are going to have the application oriented or domain specific. So when you want to build some application which is specific to that particular processor or that particular application, we are going to make use of the microcontroller. So now when it comes to the microprocessor does not contain a built-in IO port. Okay. So your microprocessor does not contain a built-in IO port. IO port is nothing but what? So where you are going to have the input and output operations. So as we told that the microprocessor will not be having the external input and output port. So you have to fix then IO port will become the dependent unit of the microprocessor. So that if you want to communicate from the outside world to the inside the microprocessor, or if you want to communicate from the inside to the outside, how you have to communicate? So you have to communicate with the one external device which you have to put, which is called as PPI 8255 PPI. So that PPI stands for Programmable Peripheral Interface. So that is normally called as 8255 PPI is the IC which you are going to have. Okay, so 8255 PPI you are going to make use of to do the IO operations to be when you require IO operation to be implemented. So you will see 8255 how it is going to work in the future. So what are the different ports it will be there for 8255, how it will be communicated, that you are going to see as part of your curriculum. Okay. So now here when you talk about the microcontroller, so in the microcontroller what will happen? The most of the processor contain multiple built-in IO ports. Okay. So the most of the processor contain multiple built-in IO ports which are operated as a single 8 or 16 or 32-bit ports as an individual port pins. Okay. So here you can see that most of the processor, most of the microcontroller, okay, which you are going to have, it will be having the built-in IO ports, built-in IO ports. So now those IO ports which are going to have, either it can work with respect to the single 8-bit or 16-bit or 32-bit ports on the or an individual port pins. Okay. So if you take the microprocessor, it will be used for targeted for high-end market with where performance is important. Okay. So if you take the microcontroller, so it is going to be targeted for embedded market where performance is not so much critical. So now this is at present the deformation is invalid. So limited power saving options compared to the microcontroller. Okay. So it is going to have more power consumption will be there for microprocessor. So compared to the microcontroller. So whereas in your microcontroller, it is going to save, it is going to consume less power. So it includes lot of power saving features. So next comes to DSPs. Okay, when it comes to DSPs, so DSPs nothing but what? They are powerful special purpose. Either it may be 8-bit, 16-bit or 32-bit microprocessor designed to meet the computational demands and power consumption. What do you mean by computational demands? Computational demand is where your computation is more. If when you build an application, if that particular application requires more amount of computation, then you are going to make use of DSPs. That is digital signal processor. So if you take the microprocessor also, you are going to have the DSPs inside that one. So even the mobile devices will be having that one. So now if you take this particular DSPs, so how the DSPs is the DSP is nothing but what? So they are compared to your general purpose processor, it is processors are 2 to 3 times faster in signal processing applications. So when signal processing applications comes, so when the signal processing applications is nothing but where your mobile devices. So if you are using your normal microprocessor here, the communication, the signal processing will become uh, the time taken to process the signal will become less. To have more signal processing, so we are going to make use of the digital signal processor. So if you take the digital signal processor, basically it is 2 to 3 times faster than the general purpose processor. Okay. So now if you take the DSPs, digital signal process, it implements the algorithm in the hardware. Okay. So when you are talking about the device, so DSPs, so you can improve the performance either in the code or you can improve the performance in the design of the hardware. So how you are going to design of the algorithm? So now whatever the algorithm you are going to design to improve the performance, so it is going to be DSPs implements the algorithm in the hardware. Okay, where it speed up the execution. So where it is going to speed up the execution, whereas GPP implements the algorithm in the firmware, where the execution depends upon the clocks of the processor. As I told you that how the clock is related to the speed. Okay, so as I told you that the execution depends upon the clocks of the processor. So already we have seen, already I have explained that how it will be dependent. So if you take the processor speed, if you take the processor speed, for example, always the processor speed will be calculated in terms of frequency. So frequency, if it is 2.4 gigahertz, so the time taken will be 1 by f, which will be 1 by 2.4 into 10 raised to 9. So that will be as the same example I am giving, that's it. Don't worry about that one. So it is nothing but 0.59 seconds. That is the time taken to execute one instruction. It is time taken to execute one instruction. Execute one instruction. Now if if it is nanosecond means what? It's a minute of part of the second. So the processing will be fast at that time. Okay. So that is how it is. We are going to tell you that. So that the DSPs it is going to perform the depends upon the clocks of the processor. So if the clock speed is more, the time taken to execute the instruction will be less. So if the time taken to execute the instruction is less, obviously the performance of the system will get improved. Okay, obviously the performance of the system will get improved. So your whereas if you take the general purpose processor, in the general purpose processor, actually the algorithms will be implemented in the firmware. Whereas in your DSPs, okay, that is a two difference. You can see it here. If you take the general purpose processor, the algorithm, so if you take the general purpose processor, the algorithm is used in the hardware to speed up the execution. If you take the if you take the DSPs, okay, sorry. So if you take the DSP, so DSP implements the algorithm in the hardware to speed up the execution. Whereas if you take the general purpose processor, it is going to implement the algorithm in the firmware. Okay.
Sir, your voice is not audible, sir.
Why? So now, if we take the DSPs, so your DSPs are microchip design. Okay, so your DSPs are microchip design. Now it's audible, right? Hello.
Yes, sir.
So your, what do you mean by DSPs next? When it comes to the DSPs, as we are told that they are microchip design, basically used for performing high-speed computational operations. Okay, so Microsoft DSPs are microchip designed for performing high-speed operations for addition, subtraction, division, and multiplication. Okay, so that's how it is going to be performed. So next, what are the different units of DSPs? If you take the different units of DSPs, it contains the program memory, data memory, computational engine, and IO unit. So these are some of these units will be common in all the processor or microcontroller. The program memory will be there to hold the program. The data memory should be there to hold the data. And apart from that one, you are going to have the computational engine and IO unit. So if you take any processor or microcontroller, program memory, data memory will be there. Okay, so that you keep in mind. So if you take the program memory, it is used to store the data required for processing the data. Data memory is there, nothing but memory used for storing temporary variables and data which is required to processor. Next is computational engine. What the computational engine requires? So the computational engine, so as the name indicates, computation. So computation is nothing but what? We have to process the data. So it perform it was perform mainly DSPs are we are using in signal processing applications, right? This DSPs are going to be used in signal processing applications. So now in the computational engine, it is going to perform the signal processing in accordance with the stored program memory. So in the program memory, what I have been in the program memory, I have stored that what are the operations to be performed. Okay, those are the instructions which will be stored in your program memory. Depending upon the instructions which is stored in the program memory, so your signal processing unit or computational engine is going to perform that particular actions. So now here, if you take the IT, so it may includes arithmetic unit which runs parallelly to increase the execution speed. So if you take the DSPs, in DSPs it's going to have the arithmetic unit which runs parallel to increase the execution speed. So if you take the IO unit in your DSPs, so basically if you take the IO unit, it is basically used to capture signals to be processed and deliver the processed signal. Okay, it is basically IO unit. It is used to capture the signal to be processed and deliver the processed signal. So this is the difference between RISC versus PRISC. Next. Okay, so I think RISC and CISC I have already discussed in your class. So again, I don't want to discuss. So can you tell the difference between RISC and CISC? What do you mean by RISC? What the RISC stands for? Can anyone answer? What is RISC? If we start talking about the RISC and CISC, what is the RISC abbreviation of the RISC stands for? Already you have written this particular difference in your first IA only. Difference between RISC and CISC. What is RISC? Can anyone tell? Abbreviation of RISC stands for Reduced Instruction Set Computer, whereas your CISC stands for Complex Instruction Set Computer. As I told you that in the RISC design philosophy with respect to the ARM, so how it is going to be designed. So you are going to have most of the instructions will run single clock cycle, where in your CISC it's going to make use of the more number of clock cycle to run a single instruction. If you take the CISC, Complex Instruction Set Computer. Okay. So now, if you take the RISC architecture, it will be having lesser number of instruction. Okay. So, and then since how the RISC will operate basically on load store operations. Okay. So if you take the RISC architecture, it's going to work with the load store operation. So because you cannot manipulate the data inside the memory. Okay. Whereas it is not the case with your CISC. CISC can be operated directly on the memory. Okay. So that is one instruction. So if you take the RISC, it is going to have the lesser number of instruction. If you take the CISC will be having the greater number of instructions. So if you take the RISC, what is how we are going to achieve the instruction parallelism? The instruction parallelism is achieved through pipelining in your RISC architecture. Whereas if you take the CISC architecture, you will be not having the pipelining option. So no instruction pipelining feature is there in your CISC architecture. Okay. So here you are going to have the orthogonal instruction set. So here, what do you mean by orthogonal instruction set? It is all side. So that means it allows each instruction to operate on any register and use any addressing mode. So it is going to, generally they are going to tell that one, but even they are having the limitations. In your ARM also, you are going to have the limitations that we have to work with respect to R0 to R13 only, the register. So, but it is not the exact RISC machine. So it is advanced RISC machine. So there is a difference between your RISC machine and the advanced RISC machine. Don't compare your normal RISC processors, that is your microcontroller 8051 with ARM. ARM is an advanced RISC machine. Okay, so that you have to keep in your mind. So that's why is most of the RISC architecture which you are going to have. So it will allow instruction to operate on any register. So it will tell you that that particular instruction can operate on any register with any of the addressing mode which you are going to have. So here in your CISC, if you are going to have, it doesn't have the orthogonal instruction format. That means all instructions will not on all registers. Okay, so not operate to allow on any register. For example, if you take some of the, you only have written in your first IA, some of the programs where you have copied and downloaded your 8085 processor. So your 8085 is a CISC architecture. There you are going to have the LHLD instructions you have been used. So if when you are used the LHLD instruction, so that is HL refers to it is operating only on particular register, right? So that is it is going to operate only on HL register. So apart, but where it is voiding, it can, that particular instruction can operate on any register. So now there are some instruction load A, load B like that and all, which will load the data into the accumulator only. So it is not, we are not specifying to load the data into a specific register. Okay. So wherever if you take the RISC architecture, since it is a load store operation, whatever the operations you are going to perform, the performance of the operation has to be done inside the register only. Okay. So in your CISC architecture, the operations can be performed on register or memory dependent on the instructions. So here the large number of registers are available in RISC. Limited number of general purpose registers are there in your CISC. So programmers need to write more code to execute a task since the instructions are simple one. So here the programmer can achieve the desired functionality with a single instruction. So, but it is going to have the effect. So here in the RISC, it is going to have the fixed length instruction where it is going to complete its execution in single clock cycle. Where in a CISC, you are going to have the variable length instruction, and each instruction is going to take more than one clock cycle to complete it. So less silicon usage and pin counts. Here more silicon usage since more additional decoders logic is required to implement the complex instruction set computer. So it will be the RISC machines only designed to be using the hardware architecture itself. Okay. So when you come to RISC, it will operate it only on the hardware architecture. Okay. So we are going to have the two types of architecture. One is hardware architecture, other is von Neumann architecture. So what's the difference between hardware architecture and von Neumann architecture? Can anyone tell? What's the difference between hardware architecture and what is the difference? Which one will be having the separate bus, separate unit for data and instruction, whether you are Harvard or von Neumann? Okay. So in your
hardware.
Yeah. So your hardware architecture will be having the separate data path and the separate instruction path. Okay. How in hardware architecture. Whereas in your von Neumann architecture, the data and instruction bus, the bus is shared by both instruction and data. So that's what the difference between these two. So I think these two things you know already. So this is the difference what they are going to tell. So I will stop the class today. Okay. Whether I have to do this one now, whether you will read by yourself. one human and hardware, and we will see what you mean by one human or one human processor, hardware or one human processor. That I will go in speed only, since already you know this one in your computer organization. So I don't want to waste much of the time of yours. Okay. So anybody having any doubt till now? So you should know what is the difference. That's it. So it's a purely theoretical part. Okay.